Hello, everyone. Thanks for joining. Today, we'll be talking about how we leverage Apache Airflow as a orchestration tool to build a distributed pipeline with Jupyter Notebook. Here's the agenda. Firstly, we will talk about the background on how we build notebook kernels as Docker images and then deploy them in a Kubernetes cluster. Then we will go over approaches to orchestrate notebook jobs as a pipeline. These includes notebook UI, Magics, and the REST API. These will be followed with a short demo. Then we will briefly talk about the architecture on how Airflow is deployed on Kubernetes and how we leverage Helm as a tool to help with deployment. Then we will close it up with the summary. My name is Weijun. I'm a software engineer in AI ML platform at PayPal. Join me is Karthik. He has over 12 years experience in building distributed system and applications.
Last year, our focus was primarily on containerizing Jupyter Notebooks app and implementing Kubernetes to modernize our existing notebooks infrastructure, which was incumbent to eliminate many of the manual processes involved in deploying and scaling our legacy monolithic multi-tenant notebook infrastructure. In this talk, we will present you a few architectural tidbits from our journey through this. Our old native setup involved centralizing notebooks using multiple Jupyter Hub services on a highly available notebook server grid platform, deployed on bare metal servers and used NAS as shared and decoupled storage layer. Our end user typically accessed notebook environment through a load balancer. A single Jupyter Hub can spin up multiple notebook servers, typically one per user, with shared CPU and memory resources. Now, with this setup, we encountered a few issues which galvanized our modernization effort. We often encountered resource contention, especially in terms of memory during peak hours, and paucity of a disk quota management required us to have additional housekeeping managing the disk space. Lack of GPU support was an impeding factor for data scientist group as it required them to switch to a different environment to use GPUs. Apart from those, we also had the operational challenges such as limited scalability, maintenance overhead, and feature limitations like no support for remote kernels. Architecturally, we made three key changes to circumvent the issues. First, as you can see, we containerized all our notebook processes, Jupyter Hub, notebook servers, and remote kernels, which enabled us to scale up and down with zero manual effort. One of the magics of Kubernetes. Now, notebook servers are launched remotely by Jupyter Hub instead of local. Second, we introduced enterprise gateway servers, which enabled us to launch kernels in different servers, thereby distributing resource utilization across available compute resources and help us easy resource management to shared compute cluster for large number of users. Third, the PVCs. Persistent volume claim, we further virtualized and abstracted the storage, thus providing more control over the storage requirements and access per user. Jupyter Hub Services is launched as parts in Kubernetes. When a user tries to launch a notebook server, Jupyter Hub authenticates a user and launches a notebook server in the namespaces that they are having permission with. User is provided with multiple options depending on the role. Once a notebook server is launched, it will connect to the enterprise gateway to fetch the kernels. Each kernel will be running as a pod with allocated resources attached to the pod.
Now let's talk about the different ways of scheduling notebook jobs. The easiest way is to schedule a job via notebook UI. We can specify the running interval, start time, end time, and email notification. Click on the schedule button. A DAG file will be generated in the backend, and the Airflow running in the Kubernetes cluster will pick it up and run. And after the job is completed, you will be able to see the key metrics in the notebook UI itself. Now, the first approach seems very straightforward, but it do come with a restriction. That is, we cannot schedule multiple notebooks at the same time. That's why we provide the second approach, which is to schedule a job via notebook magics. We are passing a JSON configuration to the schedule magic. -A specifies a type of action, which is to create a new deck. You can also get the status of the job, update a job, and delete a job. To meet our data scientists' requirements to incorporate a scheduling feature, we provide a third approach, which is to schedule the notebook via REST API. The user would have to define a configuration file that includes the specification for the job, the tasks, and the dependencies between the tasks. And the user will pass the configuration to the REST API, and a corresponding DAG file will be generated and stored in a PVC. Now let's jump into the demo. Here is an example of using TensorFlow 2 kernel to train a convolutional neural network. To schedule this notebook, first I have to right-click the notebook and click on Schedule button. Here you can specify the interval, the start time, end time. But for testing purpose, let me run it immediately by click on the Run Mouse button and skip the email and click on Schedule. So you will see the notebook has been successfully scheduled. We can check the execution status of the job via Schedule Jobs tab here. Click on that. It will show that the job has been executed. And when we go back to the notebook, you will see that the train has been completed, and it prints out the training and the validation accuracy. So now let's see an example of scheduling multiple tasks in the same job via schedule magic. So you can see here I'm passing a dictionary to the magic. We defined the job specification, each tasks, and the task need not be a specific notebook task. Here I'm only writing some random text to the file, which is stored in a PVC. We have 4 different tasks, and here we define the dependencies between these tasks. Now let me execute this one, and we are getting a 200 response. Now we can see the status of the job by using this command. This will get the state of the job. We can see it is running, and we can also delete the job. We'll see it has removed the records in metadata DB. So now let's see the third approach of scheduling a notebook pipeline. You can see here I defined a task to run 3 consecutive tasks. These tasks are running in different nodes. The first and the third are running in CPU node, and the second is running in GPU node. So now let me go to the terminal and run the curl command to pass this JSON configuration to the REST API and hit enter. And let's go to the Airflow UI. And here you will see that these 3 tasks has been scheduled in a pipeline. Okay, so now after a few minutes of waiting, we can see the job has been executed successfully. Now let's go back to the notebook and open up the third task. Let's go down and see it has generated a poem starting from my name based on the recurrent neural network model we trained on top of the Sonnet.
This is a high-level architecture of implementing and orchestrating Airflow using Kubernetes. Let me start from the top left. Airflow has two main components, scheduler and worker. Each of these components is deployed as a pod in Kubernetes. When the user schedules a notebook, the DAG is written to the PVC that is attached to the scheduler pod. The scheduler pod launches the worker pod for each task. The task is executed by the Kubernetes operator that reads the notebook metadata and fetches the information about the image, type of compute resources needed to execute the task. Once the execution is completed, the user gets notified about the status of the job.
So in paper, notebook is deployed in different environments with different configurations. And that's how Helm comes into picture. We first abstract out the differences in configurations and store them as a YAML file. When we do the actual deployment, this YAML file will be passed to Helm and further be referenced by the config map. So in summary, using Airflow with Kubernetes executor, we were able to achieve a high level of elasticity. The number of concurrent tasks are now no longer restricted by the machine capacity. It can be easily scaled up and down based on the actual workload. We can separate the duties of engineers in the same team who are working on different parts of the pipeline. It can also be easily maintained because the tasks using different environments in the same pipeline can be isolated with the task-level pod configuration. We can also allocate the resources efficiently by separating different stages of the ML pipeline. That will conclude our demo. Thank you so much for watching.